All right, everyone, how we doing today? Doing good? All right, so first off, how's everyone doing on the assignment? Everyone doing good? Everyone started? Halfway? Everyone's finished? Submitted it? Perfect. That's good. It's due tomorrow, Saturday at 10 a.m. so I can start grading. What you mean? Nah, it's due tomorrow. Well, is it going good? Is it going okay? The reason why I was hoping it was not due later because I want to go over review for today. But if we do have questions to hopefully help you guys actually do the assignment, I will do the assignment. And if you guys want, I will stay for 2 hours if you guys need it. Because I haven't made an in-person video in a while, so I'll help you guys. But mostly I want to go over the exam review. But all right, so let me see. I should have pulled this up. Let's type in Matlab 2019. And let's see what I can do. Actually, let's pull up the actual assignment too. Let's see. EE360. Hey, there we go. That's what I wanted to pull out. And, let's put this away. And as you can see, I uploaded something at 10:49. Oh, there you go. Your little quiz that I made for you guys. Let me click through it just in case someone didn't know. Oh, this camera is a little dark. Oh, there we go. That's good. So this is something I created for you guys. This should definitely be a pretty good helper for the exam. It's another definition. I chose this one because quick start. You guys remember the definition of a function? It's a rule that maps elements from a set to another set, unique elements of unique elements of another set. There you go. So, what's the definition of a transformation? You guys remember that? It's another rule which maps sets functions from a set to unique other functions or transformations to another set. Forget where that page was. Maybe I can show you. Someone's probably barking at me saying, "You don't write anything." What page is that? No, but that's chapter 1. Let's see. Page 4. Internal system. Transformation. There we go. Where's my screen so that people don't bark? Wait, that's not it. Where is it? I just literally saw it. Internal signal. Definition. Transformation. There we go. Let's pull that there. Transformation. Mapping or operator. So just write a transformation from a set A, so think of X, of functions to a set B, so think of Y, of functions is defined as a rule which assigns to each element, the word element, in the set A, a unique element in the set B. So if you've noticed, the word element is what I'm trying to focus on. So if I were you, and if I were on this exam, what is a transformation? It's a rule. I'm going to underline it. A rule which assigns, let me see, to each element, and I'm going to underline that, and then he does this in the book, function. In the set A, but we can think of this as the input X or some function X or function. Let me write that. Function. A unique. And you better underline this too, because if you don't put unique, he's going to take off a point right there. I think it's like 5 points for each word. A unique element. And I'll just do this too. Function.
Oh, I think somebody said something in the chat.
So there's something in the chat. Let's see. 4. Oh, that was the page. Thank you, Michael. Element function in the set B. And for purposes I'm about to show you, I'm going to write Y. This is X. Where is that first book? The reason why I pulled out the first book. Let's see, where is that definition? And I'm trying to stress this for you. Aha, here it is. The definition of a function. Let's see if you guys can see that. From is a rule. So a function from a set X to a set Y is a rule, I underlined it, that assigns to each X, we can look at this, each element, see that? Each X element, a unique element. So you see a unique element. I'm trying to like show you guys some comparisons, and then there's that.
Right.
So hint, hint, he did tell me he was going to put the definition of a function on this exam, but not the way you think. So if you guys remember that. Or maybe he might throw a different definition. I don't know how many definitions there are, but that's how you would remember it. So that's one of the words I put on there. He can put other stuff. Remember the last quiz, I put a bounded signal, or he can throw in internal signal, any of the other stuff he can put on. Or he can ask you, what is a memoryless system, linearity, whatever he wants to talk about. Huh? That X? Oh, I was trying to compare. So if you remember the definition of a function, it was talking about X's and Y's. But for this definition, the transformation, it's the same. It's a rule, but instead of using X's, it uses sets A's. So the set A can have f of X, f of whatever you want, to different unique elements or functions. So in a different set B. So that can also have Y of Y, Y of Z, you know what I mean, right? So I'm trying to make this like, connection, to hopefully click into your minds. Let me get rid of that. So that makes sense. That's how you would write it on the exam. So I'm going over this just in case someone's trying to memorize this on while we're going through this. So the next question I have on here, and I pulled this off from your assignment and maybe change it a little bit, is to draw a transpose direct form 2 block diagram. And I give you this little system. So if anyone's at home and we're going to try and do this, what's the first thing we do when we have, well, solve for Y? So you got to divide the entire thing by 3. There you go. So now you have Y of n minus 1 over 2 Y of n minus 1, right? Which is equal to, what's 6 divided by 3? 2x of n minus 3x of n minus 2. There we go. And just to get you guys started on what we're defining as A's and B's, I'm going to define, well, I'm going to put a 1 right here and define this as A0. Okay? A0 is equal to 1. And now A1 is going to equal to this. I'm going to make that equal to minus 1/2. All right? And now B0, I'm going to define that as 2, which is right here. And then this one has a delay of 2, so it's not 1, it's 2. Remember that. So 0 delay, 1 delay, 2 delay. B of 2, which is equal to minus 3. So that's what I'm defining right now. So you can see other people's way of teaching systems and signals. Some people have minuses in their coefficients, some people have pluses. But the way Dr. Stuber made it in your assignment, he set it up like this. You have the Y's on the left, X's on the right, defines the constant, the coefficients as, well, A0, A1. So we can do the following. Let's do this. Y of n plus A of 1, right? Y of n minus 1, which is equal to B of 0, X of n minus, plus B of 2, X of n minus 2. All right? Now it's starting to look like your assignment. Okay? And now we solve for Y. Y of n is equal to B of 0, X of n plus B of 2, X of n minus 2, and then the minus A of 1, y of n minus 1. There we go. So this is your equation. Like, well, if you were to like do a direct form 1, well, kind of, this is how you would brute force it into Matlab. But we'll go over direct form 1 later on. But I'm asking for a transpose direct form 2. And we're looking for state space equations, which can be defined by here. I'm going to call it state equations. Equations, I can't spell. So, and then I say represent your answers in matrix form. So if you guys remember from the last lectures, the pre-recorded lectures, how I was drawing those block diagrams, why did I pick transpose 2? Because, well, that's really easy to draw. All you do is draw your x of n. Let's look at the delays. The maximum delay we have is 2. So that means we have 2 delay blocks we need to draw. And since we have b of 2, that means we're going to have a b0, b1, and a b2, ideally. So we need to have 3 wires. So I'm going to do the following. Let's draw a block right here. Do this, do this. And someone's going to go crazy for me doing this. B of 2, B of 0. So why did I draw it like this? Well, it's a procedure. So you notice that I have just a B0, right? And a B2, okay? But I don't have a B1. What's B1? It's nothing. It's just 0. If there was an X, well, it's not there because B of 1 is 0. So that means this right here is just an open. Okay, I'm trying to get you guys to think. So if you were to draw these block diagrams on the exam, if you asked for a transpose direct form 2, well, obviously you just draw it like this. It's these fingers, literally how I've been saying it. And then after that, you look at your coefficients. What do you have? We don't have a B1, but we do have a B0 and a B of 2. Okay? Now let's do the other side. Yeah, it wouldn't be there. You can naturally draw it, but me, I'm a picture person. I like procedures. I don't like memorizing stuff. Like this problem, I designed so that if you try to memorize a picture, it's not going to help unless you know how to control it or what to do. But right now, I'm actually showing you what to do. A procedure, just draw your block diagrams, B1, B2, etc. And, okay, I'll just draw this. Plus, then let's draw a delay block. Okay. Plus, let's draw another delay block. There we go. Then plus. And then this is a wire, as usual. And then let's just do it because, well, that's procedures. And let's draw that right there, right there. And this is A1 and A2. So look at our coefficient right here. We have an A1, but we don't have an A0. A2. What's A of 2? 0. It's just an open. So if you wanted to redraw it, you can, but for procedure purposes, you would draw it like this. Draw it the way you know. You've memorized all these block diagrams. There's 3 of them, times 2 if you consider the analog version. And once you got the procedure, then you can start creating equations from that.
Is it acceptable to just cross it out right open?
I'm just doing this for visual purposes to hopefully one of the students in the class is probably asking, hey, how'd you do that, or what do you do in this situation?
So is it like that? Do we just leave it as a wire, or do we just not even draw it?
So
Don't even draw that box.
actually, let me just
Or the line.
show you one thing. So the reason why I didn't draw A0 is if you watched my videos, what did I call A0? It's just a wire.
Right.
So it's just a short. It's a short. A of 0 is equal to 1. So what happens when you have a gain of 1? It's just a wire. What happens when you have a gain of 0? If you multiply, huh? Yeah, a gain of 0. It's just an open. Yeah, just an open. So that means you wouldn't even draw this. It'd just be just nothing. If you want me to redraw it for
No, you
you.
don't have to redraw. I'm just saying, can I draw a wire or no?
So if I were to draw here, well, don't draw it. There's nothing
Don't
there.
draw anything.
Don't draw anything. Don't even do this like port thing. Just don't draw anything. Just skip it.
Okay.
So this would be all gone. And the plus would still remain there because you're adding this state, which is about what I'm about to get to. So we're about to start state space equations. So hopefully if you've seen the video, you already know how to approach this. But if you haven't, the first thing you have to do is set up your state equations. So the nodes. So oh yes, they should. Please do not forget this on your assignment. So A0. So the way Dr. Stewart teaches signals and systems is he develops the gain equations from here. This is where he gets his gains. Okay, so he starts setting whatever coefficients are here. Here's a 1, here's a minus. These minuses get tucked into the coefficients to turn into this plus.
Right.
And the way he's setting up this block diagram is he's assuming this topology right here, you have a minus right here, and you would have to copy this minus, drag this minus into these blocks. Some other engineers, well, they will look at this, they will tug this minus in here and they would make this a plus, but then it would be plus in here. So it's, there's no universal way of like figuring out these block diagrams. Everyone has a different way of, like when I'm approaching these problems, everyone has 2 different ways. I'm looking at the Oppenheim book. He does it with pluses in here, but the minuses are tucked into the coefficients, whereas Dr. Stewart does it the opposite way. It's just a style, honestly. Can we draw it saying open in the test, or do we lose points? Well, I'll tell you right now, the example I'm giving you guys right now is much harder than what you'll see on the exam. So point is to stretch your brain. So if you can do this, then you can do the assignment, and you can also do the exam. So everyone should get like an ACES problem. So right now what I'm going to do, and instead of, well, he might actually not put an open. He'll just put a random number in there. I'm choosing practical numbers because we're about to program this in Matlab. So for those who haven't started the assignment or have or want another insight into it. So the next thing we got to do is I'm going to call this node, okay, let's call it Q of, should I? Let's call it, where's my skinny marker? Q of 2. Can you see that color? Pink? Or is that bad?
It's really light.
Okay. Is that better? Purple? All right, I'm going to call this node right here Q2 of n plus 1. All right? So remember from the lectures, from what Dr. Stewart was talking about, where, oh, okay, so DSP engineers like, oh, Q of n, here's a delay, and you have Q of n minus 1, right? But if you go into controls, all those controls peeps just like positives. They don't like negative delays. And I show you how to code in a controls way, but I don't like the controls way. It's weird. But universally, we all accept the controls way when we're doing all these state space equations, so thank them for that. So we're going to try and do something like this where we label a Q here, and then we have an n plus 1, goes through a delay. What happens when you go through a delay? It just minuses 1 to the time, whatever is in this equation. And let me get to that right now. So you have Q of 2 right here, right? I'm calling it Q of 2. There you go. What comes out right here? At this node right there. Q of 2 of n. Okay? Now let's label this node right here Q of 1. Do I want to call it Q of 1? Yeah, let's call it Q of 1. Then plus 1. Let's call this, and then it goes through the block diagram, right? There's a little delay. What do we get? Q of 1 of n. Okay? Make sense? Sweet. And there we go. Let's label this y of n. So to approach the state space equations, the first thing you have to figure out, or the first thing you're calculating is, so if I were to run through this circuit, okay, running through this circuit, right? I was going here, here, here. We're feeding through these gains. What's the first thing that's going to be solved for? So if you see this gain block right here, it's just a gain. It's instantaneous. The value that goes through here is instantaneous. So if you throw water here, it just immediately goes to the output. So what's the first thing we got to solve? The output. So if we were to solve for the output, y of n is equal to x of n, which is multiplied to b of 0, x of n, plus, there's a plus, whatever is that, q of 1. And there we go. So one more condition I got to set up, because I don't know if anyone's watching the state space equation videos. We're going to set it up in the following: q of n plus 1. This is a matrix. I'm just going to make it capital. And let's call it a of q. Yeah, let's call it a matrix. And c of q of n plus b of x of n plus d of x of n. So what I'm trying to show you now is we want current states and we want current inputs. Okay, so we're going to set all these equations that we're solving for as functions of current states, which is the current state. So whatever are n, as you can see, n, and current inputs. So the thing about transposed direct form 2, it's the easiest equation to solve for the output. You already have everything as a function of its current inputs and current states, or whatever is in your memory. So that's the beauty of the transposed direct form 2. But its negatives are that you have to solve for its output, or the current states itself, or the next states. So that's what they call it. This right here is I don't want to use that color. Next state. Let's solve for this guy right here. Q of 1 of n plus 1. So this is the equation we have to solve for. Q of 1 n plus 1 is going to take in 3 nodes. Well, this node right here is just an open. So if you wanted to, you can, should I? Okay, I'll do it. B of 1, x of n minus, no, just n. Okay, there we go. But you know that b of 1 is just 0, so you don't even have to write that there. It's just an open. Okay. The next node we're going to add is this minus. This is a minus sign right here. Minus a of 1, and what are we taking into this node? We're taking in y of n, which is an output. It's not an input, it's not a state. That's bad. We need to solve for this. Okay, and then, huh? Oh, there we go. Easy. And then plus, we're taking q of 2, q2 of n. There we go. So we already have, so if you look at this y equation that we have, current y input, or the current output is equal to current states and current inputs, right? But this equation here has a current output. We can't have that here. We need to have all our equations as a function of current inputs and current states. So there's one thing you can do. As you can see, you see this y of n right there? All you got to do, if you want current states and current inputs, just replace it. And now you get the following. Q of 1 n plus 1 is equal to, let's put the minus a of 1 there, and let's call it b of 0 x of n plus q of 1 n, there we go, plus q of 2 of n. There we go. Make sense? And then if you wanted to rewrite this into a better way, let's put, should I do that, or do I not want to do that? Let's do it. Minus a of 1, b of 0, x of n, minus a of 1, q of 1, plus q of 2 of n. There we go. So this right here is our q of 1 n plus 1 equation. There we go. Make sense? Sweet. Perfect. And now, I didn't make enough room on this. Someone's gonna get mad at me. There we go. Let's pull out another piece of paper. Oh, there we go. So I'm trying to show you guys how to solve these equations practically. So just in case he gives you a curved ball or an easy ball, or I don't know what he's gonna throw on the exam. Softball, hopefully. So now what I want to solve for is this Q of 2. We got to solve for all these next states. Q of 2, n plus 1. I'm going to write this down. Next state, okay, that's what it's called, is equal to, well, what do we take here? We take in this input, which is being multiplied by b of 2, x of n, plus, well, we have nothing here. If you wanted to, you can do minus a of 2 y of n. However, if you already noted, this is bad, a of 2 is equal to 0. In our diagram, this is an open, right? A of 2 is an open, it's 0. So this equation doesn't even exist. So if you wanted to, actually, that's our solution right there. Oh, messy. B2. Simple. So I'm about to rewrite. Oh, is someone talking in the chat? Diego? Should I mute him?
Yeah, I don't think he knows.
I don't think he knows. There we go. Sweet. All right. So let me rewrite these equations again. So I'm going to write it in the following. So Q of, let's do this. Q of 1, n plus 1 is equal to, and I'm about to show you this. Should I? Okay, I'll show you. Minus a of 1, b of 0, x of n, minus a of 1, q of 1, n, plus q of 2 of n. Okay? And now I'm about to rewrite the second equation, which is q of 2, which is equal to, plus 1, which is equal to, where's my second equation? Oh, it's up there. Minus b of 2, x of n. There we go. I think that's it. Yeah, that's it. Man, I made this too easy. And minus b of 2. Why did I do minus? Oh, I was looking at this. There we go. Plus. That's my fault. Now let's do the output, which is equal to, well, that's the first thing we just solved for. B of 0, x of n, plus q of 1 of n. So now the next thing we gotta do is put this in matrix form. So the format that Dr. Stupid wants is, well, let's do this. We have our q of 1, n plus 1, q of 2, n plus 1 is equal to, and I like writing it like this. Let's make the box already. This is going to be our A. Let's do this. Q of 1 n, q of 2 of n. There we go. Plus, should I? I think it's going to be this big. Yes, it's going to be that big. Of x of n. And this is our b's. So this right here is a 2-row by 1 block. And then A is going to be a 2 by 2. And then B right here, I'll tell you right now, it's going to be a 2 by 1 block. So what's the first thing we got to look at? Our Q of 1 equation. Q of 1, n plus 1. And then let's look at Q of 1. Here's Q of 1. Let's look at what this equation has. Here's Q of 1. It has a minus 1, or minus a of 1. Let's write that right here. Minus a of 1. There we go. And then let's look at the Q, the next equation. So what do we have right here? Q of 2. So we have this. So in this equation, Q of 1, n plus 1, Q of 1, n plus 1, we have the following two states. We have a Q of 1 state and we have a Q of 2 state. two current states. Here's Q of 1 being multiplied by minus A of 1, and Q of 2 of n, which is being multiplied by, well, just 1. Simple. And now let's look at the next equation, which is Q of 2 of n plus 1. So let's look at the Q of 1 states. Well, we don't have a Q of 1 state because I made it 0 by accident. And there is actually no next state. So if you see, I don't have a Q of 1 or a Q of 2 here. It's just literally this, just an input. So these are just two zeros. I should have made this, formatted it better, but if you look at the video, the last video, the state space equations, I show you a pattern. And the pattern I show you there, I highly recommend people memorizing it. It's a trick that, it's in the book too, but it's a format I'm trying to show everyone too. But if you were to throw this problem on the exam, we're just walking it step by step. All right, so we have no states in this Q of 2n plus 1 equation. There's no states at all. It's just 0. But we do have a B of 2 term. Actually, I didn't even cover this one. Why didn't someone should have told me that? Here's this input right here. We have, for the Q of 1 n plus 1 equation, right? I forgot to take care of the inputs. We have just one input, which is just minus A of 1, B of 0, right? So I completely forgot to take care of that one. So that's how you do your first equation. Now your second equation, well, we only have one input, which is just B of 2. There we go. And that comes from, let's just draw spaghetti. There we go. Simple. So there we go. We have our state space equations, well, for our next state. And then for our y's, y of n, well, it's just a 1 by 1 matrix. However, we have the following block. Q of 1. The way I'm drawing it right now is how I do it on all his exams. I always draw these blocks first. The current states first. Like, you see this matrix? Really easy to plot. And then this right here is, I think, just a block. Is it? I'll remember it. Yeah, I'll just put the input right there. I think it's just one block. Yes, it's just a game block, sorry. So if we look at our y equation, our current output equation, which is this, we have one current state, which belongs to Q of 1. So here's Q of 1, here's y of n. What's the first thing that goes here? Q of 1 is being multiplied by 1. Do we have a Q of 2 state? No. There you go. And I think this is guaranteed for all transpose direct form 2 blocks. There's always a 1 followed by a bunch of zeros. Read the book. You'll see the pattern. And then what's our input? Well, our input, here's our current output, current input. What do we have here? B is 0. And all transpose direct form 2 block diagrams, they have this format. I want to show you guys this. Oh, oops. You guys got to tell me that. Make sense? That's why I was saying this video camera might get in the way. Do I want to show small act? Nah, whatever. So, if you were on the exam, and if you wanted to see the matrix form, this is what you would box. Okay. And I'm telling you this right now because I think he does say he wants it in matrix form. Well, he wants it in the state space form. So obviously you need to have matrices. So if you do it like this, like write the entire thing down like the way I have it boxed in the screen, that's great. And that's what I should push everyone to do. But if you just give these blocks, well, you can switch these two, this Q01 and this Q02, you can flip it, but that means everything gets flipped. So I think, yeah, if everyone just writes what I have right here, all these Q states, the next states, current inputs, current outputs, then you should be golden. Everyone should get 100 on this problem. All right? So the reason why I gave this type of quiz is to get rid of everyone who's trying to memorize these exams. So this is to stretch you guys' brain. Huh?
You put the numbers back in, the A1 and B
Actually, yes, you should put in the numbers. Put them all back in because you see this right here. If you wanted to put the numbers back in, okay, because everyone's asking for it. Do I have a different marker? Let's use blue. So what do we have as a of 1? What did I set as a as 1? A of 1. A of 1 is negative 1/2. So let's put, well, you have a negative times a negative, you get a positive, so it's just 1/2, right? I'm going to put that right there. And that's a 1, it's 0, 0. Now we have this condition right here. We have minus a1 times b0. So what was b0? b0 was right here. I should probably just write this on the side. B of 0 is equal to 2. B of 1 is equal to 0. B of 2 is equal to minus 3. A of 0 is a wire, it's just 1. A of 1 is equal to, oh, someone's asking what I'm doing. A of 1 is equal to, what did I do? Minus 1/2. A of 2 is equal to 0. There we go. Alright, just to help me out. So we're going to solve for this one right here. A of 1 is this minus 1/2. Yep, minus 1/2 times B of 0, which is this 2. So 2 divided by 2 is just 1, and then the negative and the negative gives you a positive. So this right here is just going to be a 1. Make sense? And then all we're left with is, well, this is 1, 0. This is our B0 term. And what's our B0? 2. And there you go. So once you put in the numbers, thank you, Peter, for that. Now you have your final solution.
Don't we have a B2 over there?
B2. Oh, I didn't see this one right here. She's talking about this one. So B of 2, well, what's B of 2? Minus 3. There you go. Okay, because this is getting really messy. You guys like quality notes? Alright. Let me just pull out another piece of paper.
That was a good question, Peter. Thank you.
Definitely a great question.
Because I would have left it as A1.
Oh yeah, that would have been bad. Oops, sorry. So if you were to go on the Dr. Steerberg's final exam or his next exam, rewriting everything, q of 1, n plus 1, that's q, q of 2, n plus 1, 1/2, 1, 0, 0, that's our A. Write this down too, 1, plus 1 minus 3, x of n, and then, which is just a 1 by 1 matrix, 1, 0, which is your C, that's your B. Write this down, q of 1, n, q of 2 of n. There you go, can you see that? And then plus the 2. Easy? And this camera right here is annoying me. There we go. Let's move it there. Ah, that's better. Simple. So this is what you would put as your final solution to the problem. There you go. Easy numbers. And I'll tell you now, he's gonna do that on your exam. He's gonna put he's gonna make a of 0 be equal to, well, some different number. It's gonna equal 2, 3, 10, or whatever. There's no calculators on the exam, and he's gonna give you really easy numbers. If you're getting really bad numbers, like 1 divided by 7, then something's a little off. So I would check your mathematics. Oh, I think someone did ask that question. Can we leave the matrix with variables? And no, I would recommend writing out the actual numbers, because the number he's going to give you is as simple as this: 1 over 2, 1. It's really simple numbers that you can punch in. Maybe the answers are going to be like 1, 2, 3, 0, or something like that. So really simple numbers. Okay, makes sense? So the reason why I was trying to write it like this, and actually this is why I post content online. Let me get that out. So David's web page, courses, EE360. I'm pulling up your guys' stuff. Let me show you what I was trying to do. Just a PowerPoint it right now, because I know we got to go over some more stuff. And I highly recommend watching this video. I literally walked through a solution for you. And let me see. Where is it? Okay. You see this cyan colored thing? I was trying to get it in this format. I have a B1, and if you watch the video, I was really slow, and I was really forcing a pattern into your guys' brains. And you see this color I'm trying to do? X of n, b at 2 minus a at 2, b at 0. See that pattern? Well, I didn't color it like that. I was saying, oh, if you see the pattern, you can just easily skip this exam and just get 100. Yeah. And then I was showing you these states. Here's minus a of 1. Here's minus a of 2. You see this? You see the pattern? There you go. And then I was trying to show you guys, oh, look at that. There's a pattern. Look, b of 1 minus a of 1, b 0. See that? So I would highly recommend watching that video. I walked through how to tackle this type of problem, because this can be on the exam. You can either throw this one or the direct form 2 block diagram. They both have their patterns, trust me. So that's why I'm trying to make sure that if you do the assignment, let me move that down, that if you do the assignment, homework assignment, say 2, well, you can do that too. Exercise 4, I make everyone, you have to redraw these block diagrams and grab the state space equations. Can you do that? And you'll see a pattern. Use the coefficients. Don't solve for numbers. Just look at the coefficients, and the answer is in the book. All right? So does that make sense for everyone? All right, and now someone's probably asking, hey, how do you even do this assignment? And that's what I have right here. So from, I prepared this for everyone today. So what I did for everyone is I do the solution for you guys. So I love making functions. I like making functions. So this is a function I did that will do all the calculations you ever wanted to, but I'll show you guys what to do. And if you want to see how I built this function, you can check an old video I think I did, but I'll show you guys the procedure. Actually, yeah, let's copy that. We're going to try and recreate this function. So if you were approaching this assignment, so let me show you what I have. We only have 2 states. We don't need this guy. There we go. Wait, why did I erase that one? Q of 1, so that everyone doesn't think, oh, this is the holy solutions. No, that's not the holy solutions. This is, well, how you actually get them from your state space equations. All right. So to walk everyone through how I did this function, and you guys can do too, these right here are your gains. Gains. So B0, B1, B2, I'll erase that one for function purposes. There we go. So these are your gains. And then let me just erase that. I was just trying to get the assignment done. Let's make this one 2. So someone's probably asking, why did I put 2? Why did I put 3? What's this number right here? If you look at the previous video, I call it pre-length, where our pre-length is equal to the number of delays. Number of delay blocks. Okay, simple. And then this right here is end length. Okay, which is equal to 50, which is what he's asking for. Okay, equal to the end of time. All right, so now you have time itself. And then the way you create your state equations, or pre-allocate memory. This is an input. Let's see. Pre-allocating memory is actually, let me explain the input. So what I'm going to do for this system that we have right here that we've derived from, and I don't like it how this one's down there. Let's move that right. Come on. There we go. Sweet. And where's the other stuff? Camera. Wait. Yeah, that is my camera, sorry. Where is that piece of paper? So this right here, okay? We have 2 delay blocks. We have 3 gains. What was I trying to say? Oh yeah, we're about to throw an impulse response. We're about to throw just a Kronecker delta, just a delta function, just a spike at time is equal to 0. So this right here in the middle, if I were to just show you guys let me just comment that. This position right here is for n is equal to 0. This 1 right here, this measly 1 right there, is our n is equal to 0. All right? So we're trying to create delays because Matlab doesn't like it when you have a minus array index. So this value right here is going to be the size or how many delays we've had in our block diagram. So pre-length. So what I'm trying to show you right now is, let me write this down because I hope someone's, if you watch the videos, oh, what did I do? Oh, get rid of that, close. And I go over it more in detail in the video. We're about to throw at n is equal to 0 a delta function. However, how many delays do we have in our block diagram? We have 2 delays. So that means Matlab is expecting an n minus 2 condition. But in terms of allocating memory, it doesn't like negative array indexes. So we have to play with the zeros function. So we have to put 2 zeros before our input or before our delta. See, here's our 1. So if you were to naturally do the assignment, in an ideal world, this would be n is equal to 1. But because we have memory, what's n? When n is equal to minus 1, it's going to call this one minus 1. It doesn't exist. So for pre-allocating memory purposes, we have to do the following. Yep, actually, let me erase that. Okay. We have to do this. Our pre-length, which is equal to the number of delays. Okay? And I'll just comment that right there. Number of delays. And, there we go. Okay, and then this value right here is length to the end of time. So that means this right here can be replaced with end length. Easy to code. So once you develop this code, then everything else becomes really simple. So here's our Q states. Here's Q1, here's Q2, here's Y. All you do is just copy this. I'll show you this. Call this one Q1, all right? Actually, I'll call it lowercase 1, Q. And then you know we don't have a delta function right there, so all you got to do is just call it a 0. You can do that, or you can do it the other way, which is just putting an end length plus 1 to count for that middle 0. So there's 2 ways of doing it. You can either do it this way, or you can do it this way. Let me show you. Come on. There you go. 0 and wait, that's zeros. Zeros, and there we go. Allocating methods. Method 1. Allocating method 2. So locating memory. So there's 2 ways of doing it. You can either just tuck in this 0 into here to get plus 1, or you can just if you like looking at this right here, you can just put the 0 here and then do it like this. So there's 2 ways of programming. I'm trying to show. Are you guys seeing this? Is this making more sense? All right. And then the same thing can be done with the y output. Y, and then why did I put absolute of n of 1? So what is n of 1, or what's the first number? It's -2. So if there's a 2 right there, and this is already 2, I'm just doing the absolute value. So that's a shorthand way of like saving a lot of memory. Instead of creating this extra memory value right here, you can just directly pull out the value from wherever you need it to. So this is actually, okay, this is the third method. Yeah, now you guys are getting your money's worth. Allocating method 3. All right, now you guys have 3 ways of doing it. This is where people start splitting off on how they want to make their codes look really unique. And why did I put a Q1 there? Right. Any questions at this point? Nope. All right, we're going to keep doing your guys' assignment. All right, so...
And then just send us all of it.
Okay, yeah, that's actually what I'm going to do. Like, literally, I'm going to post this code after this. So.
Oh, okay. Why are we starting at -2?
-2? That's how many delay blocks we have. We have 2 delay blocks. If you punch in for, let me just show you this. Okay, I'll talk about it. Where is it? Boom. So if you were doing your for loop for I is equal to, how do I want to show you this? Pre-length, should I do it? Actually, let me write x, no, q of n. Oh, come on, q of n is equal to, let's just do q of n minus 2, okay, right? So if you punched in, what do we do? So what I'm trying to tell you guys is this right here is it's an array, it's a matrix, it's a vector. So if you were to look at position 1, how do you get this right here to be 1? So n would have to be equal to, okay, so what I'm trying to show you is n minus 2 has to equal 1. This is the first array index. So how do you get this to be 1? Well, n has to equal 3. All right? Oh, someone's talking. Because I know what's going on. Yes, post it, yes. Yes, I do post all these videos, PowerPoints, and all this lectures. I'm going to post this code too. And if you want, I literally post the solutions online. The last 2 pre-recorded videos do have solutions to the assignments. Hopefully people are watching them, and I'm going through another solution. I'm literally doing exercise 4, like an alternative way, but in code. So what I'm trying to say is, here's a -3, right? So what I'm trying to get to you is -3. Is that how I want to explain it to you? Because you're asking about why is it a -2, right?
Yes.
Pre-length plus 1. So in an ideal world, in the CS world, all matrices begin at position 0. Right, so you don't have to put a +1. So you can do for I is equal to 0. Okay, that means you can start accessing a of 0, and it doesn't break. However, in the Matlab world, you don't have this array index 0. You have an array index 1. So all your codes will have this pesky code or pesky number. For I is equal to 1. Everything begins at 1. So here's this 1, right? Here's this 1 right there, right? I put a +1. So what is this value here? That's our pre-length. And what did we do? What did I say right here? Here's our delay blocks. We have n minus 2, 2 delays, right? And I'm trying to say force this to 1 because we're at Matlab. N minus 2 is equal to 1. How do we force this to 1? What number does n have to be? N has to be 3. But 3 can be dissected as 2, how many delays there are, plus 1. Does that make a lot more sense? All right, there we go. So instead of forcing numbers, we're going to build powerful code that everyone can use. I was just making sure. Yes, there we go. So back to our Matlab. So this right here, you can either do it this way or, so that everyone understands what's going on, pre-length. All right, this is how many delays we had in our block, and this pesky 1 is due to Matlab having an array index of 1. And then this right here, whatever you do to the beginning, you have to do to the end. And then I'm going to post this right here too. And this right here is the end length. Okay? So this is our end of time. So, okay, if we began here, then we have to add whatever we have to the end. All right, so if this was from 3 to, it should be 50, but in reality we can't do 50. We have to go plus 3. Because if you do, how do I want to explain this? Let me show you what I mean. This is 3. There we go. Why are we doing this? Why are we adding this? For the following reason. So if I have a vector q, right? And we just define that n is equal to -2 and then -1 dot 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 to, okay, this is going to be something, some state 1 to a position, right? But if we go to 50, the position here is actually not going to be 50. It's going to add 3 more things. So instead of it being 50 here in time, right here, the position is going to be 53. Because due to the 0, let's write this right here, the 0, and here's 3. So the reason why it's 53 at the end is because this position 1 goes to here, this goes to here, and this goes to here. The consequence of why this is position 53 or 51 is due to this. This 0 always gives you a +1 for all your time, and then these 2 come from your delays. That's why we have this number and not this number. Does that make sense? Perfect. So this is how you should approach all your assignments. So that's why I did this. If you put 50 there, you're not going to get all the values. So what I'm trying to show you is, let me show you. If you just stop at 50, in terms of position, so 50, you're not going to get n of 50. You're actually going to get n of 47. All right? Makes sense? But Dr. Stuber is asking for 50. So how do you get that? You have to add 3 more numbers, which comes from the beginning, all these pesky 3 numbers. There you go. So that, and just in case someone was saying, I'm not getting n of 50 or something like that, you're going to get n of 47 if you don't add this line of code right there. Making sense? We're dissecting this really hard. So now that you have this for loop, copy it. Just copy it. I'm telling everyone, just copy it. Your assignment for all the block diagrams will use the same for loop. So right now, I took all the hassle out of your guys' minds. So literally, just draw the block diagrams. It should take like 30 minutes or less than that, depending on how good your art skills is. And all you're doing is just changing this middle stuff. Okay? So I've already taken the headaches for you guys. So as long as you do this, and understand why I did this, there's 3 ways of doing pre-allocating memory. And all you got to do, and I give you the for loop, your responsibility is just taking care of this. All right? Transpose direct form to block diagram. Yes, definitely. So now we got to actually solve for the state space equations themselves. So to solve for that, first let's do this right here. Okay, let's look at this. How do I want to do this? Okay, because this matrix form is bothering me. Like matrices are good, but I like these equations. See these right here? Let's box this right here. Implement in Matlab. Okay, so we're just gonna copy and paste everything we see here. If you were to do it the controls way, you have to actually mess with these numbers in the middle. I highly don't recommend it, but literally you're just copying and pasting from this code. So first thing we got to solve for is the y output. That's the first thing that needs to be solved for. So from, okay, let me just put this on the side, and oh, come on, I did it again. There you go. So y of n is going to equal b of 0 times x of n plus some q of 1 state. So just to get everyone there, let's do b of 0, x of 1, or the first value. This is how you do x of 1. And then this right here is a q of, what did I put? Q of 1. There we go. And then the next state, it's not, we can't solve for that one. Gotta solve for this one. There we go. Q of 1, let's make that a y, is going to equal, let me pull this out. Q of 1 is going to equal minus a of 1, b of 0 times b of 0, x of n minus, we're just typing all the way. So I'm going slow, which is bad because we should be going over some more material. I did do it in this format. That's the pattern you guys are noticing. But if you don't notice that pattern, minus a of 1 dot times b of 0 dot times x of capital X, because that's what I defined it as, 1i. That's a current input. We're looking at the current whatever value, whatever our for loop is at. And then what I do, let me see, minus a of 1 dot times q of 1, 1i plus q of 2, 1i. So why am I doing this 1 of I or something like that? You guys can do a column vectors, which means instead of doing it, I'm doing row vectors because I like rows. And what do I mean by row vectors? Let me show you. Let me run this. Evaluate section. This is what I mean by row vectors. Q1. You see something like this. See a row. But you can also do a column, and if you do columns, instead of doing this format right here, this is how you instantiate rows or call from rows. You can just get rid of that if that's much more easier for you, if you like seeing just columns. But remember, they're columns, so if you're doing matrix multiplication, do consider that. Think of what you're doing with matrix multiplication. But because we're doing with rows, that's what I'm doing. So there's two options. So if you do columns, okay, I'll show you guys. Switch this around. So instead of this, do pre-length and that to instantiate a column. Then to get a column, okay, I'll do it for you. Zeros. Get rid of that. 1. Let me run this. F9. Q1. And now you have a column. Really cool, huh? So instead of doing this, now you can just do this. Hey, take care. All right? All right. Make sense? So there's two ways of doing it. And then here's this. Now we got to do Q of 2, 1i plus 1, because we're solving for the next state, is equal to, what did I do? Just b2 dot times x of 1i. There we go. And just to verify, Q of 2 is equal to B2 times X, the current input. All right, makes sense? And now let's post this. Is it ready? Run it. It doesn't say I've defined X. That's because I define it as capital. There we go. So your quiz, the quiz that I've made for you guys right here, this block diagram, and I had to do it again. I had to like actually verify this. Will give you this. Really nice, right? Here's that, let me zoom in. If you go here, here's that -2 because of the delays. You got to instantiate that delay. And then here's our Dirac delta or Kronecker delta going through our system. What's the value? It's y. If the output at x is equal to n is equal to 0, it's 2. Why? Because, where's our block diagram? Here it is. So this is a 1, right? Well, that shouldn't be a minus. That should be a plus. But point is, this B0 is equal to 2. That's the reason why you see this number right here pop out, a 2. That's the first number. And then you're probably saying, why does it settle to -2? So there's a trick I can show you guys, but I don't know if you guys want to see that. But it's something we're going to tackle in the Z transform. So point is, this code right here, if you can do this, let me point. If you can do this system, everything we just did right here, you see this right here, this everything in this black box, and I gave you guys the for loop already. Really simple, right? Which means you guys can do the direct form 2 implementation. It's literally the same thing. All you got to do is, actually, if you guys want to, I'll do that. I got to change my page numbers. Gosh. 3, 4. Okay. Yes. So if you wanted to do the the direct form 2 block, okay, this is the hardest one to draw. Plus, the A is 0's first. We got this, let's call it Q of 1, or Q is 0, whatever you want it to be, and plus 1. There we go. Pull this down. This is the hardest block diagram. I don't like this one.
With the delays in the middle?
Yeah. No. This is the one where it starts with a plus. I don't like it. It's not like, you remember the ones I was doing fingers? I was like, June. But this one's the painful one. A of 1. That's why it's taking me a while to draw it. And don't forget to draw your arrows. Oh. D. Oh, I hate this one. This is why I didn't make it a quiz. B a 0. Yes, I'm doing your assignment. Plus. Oh, I hate this block diagram. Yes, you guys have to do. This is what I mean by tedious. So it might take you like twice as long. Okay, there we go. Simple, right? So if you were to do this, if you were to redo this assignment, here's Q of 1. What happens when it goes through here? Q of 1 of n, right? Just minus 1. Right here, okay? Right there, okay? Oh, you guys can't even see that. Okay. So now, remember how we were saying from the beginning, okay, everything before the block must have this plus 1? We're going to keep that topology. So right here, right, is Q of 2 of n plus 1, right? What's the value right there? Q of 2 of n. And there you go. Now you're ready to resolve this problem once again. And what's the first value you got to solve for? Well, actually, why is this y? You got to solve for a Q of 1. That's the first thing you got to solve for. So when you're doing your assignment, when in doubt, if you're coming through a problem where you're getting nothing running in your code, play around with the position of this. I'll show you. What happens if you put this output at the end? Like, oh, I'm going to be cool. Like, do this. And let's do it right here. This is natural. Everyone should do CLC, clear variables.
Clear
Clear variable, actually. No, that does the same thing too, actually. Okay. Just to be sane. Clear variables. So that's what I like. That's my function. So, and it actually works.
I know, I'm like, what?
Yeah, that's what I was shocked.
Same.
It should break. I don't like this.
What's going on?
Well, I guess actually, you know why? Because this Q of 2 is being solved for. It's got a current input, so this can automatically be solved for. Q of 1 is a current state, which is always 0. And then the next state, actually, no, this is actually not going to break because the next state doesn't care about what we are right now. It just cares about the next thing. So we're always solving for the next thing. So actually, all these next state space equations, they don't care about what's next. They care about what's now, and everything now has already been solved for, 0. So that means this is always solving for the next value. So actually, the position of this actually doesn't even matter. It's actually pretty cool. Okay, so there you go. It doesn't matter. But for the linear difference equations, you're actually solving for something previous. And did I do that right here? Yes, and this is already up online too. Right here, and actually we'll run this too. Okay, let's run this. So the solution to the rec form 2 actually did this for you guys. So here's your system, right? Yay! Well, I copy pasted this 3 times. Here's at the rec form 2 block. What happens if you switch it? This one should break. It should break. If it doesn't break, there you go. It broke. See, you're not getting the same response. It's giving you something different. See, if you zoom in right here, this is not running anything. So that's what I'm trying to say. Like, oh, play around with the position of these vectors. If something's not running, it's probably because it's not being solved for and it's giving you 0, 0, 0 all the time. All right, who's saying in the chat? Gotta head out. Likewise. Thank you, David. And yes, it's almost 7. See? Simple. All right? Okay, and someone's probably panicking. Okay, actually, this is a DF2, okay? Oops.
I like that one though.
Huh? The rec form 2?
Never mind, maybe I don't.
I hate this one. Because, okay, did you see how lightning fast, like, rewatch the video. Did you see how lightning fast I drew this? Like, and if you watch the state space equations, I'm like, I drew this in like 10 seconds or closer to that. This one took me like 5 minutes or something like that. This one, I don't like this one, the rec form 2. Okay, so, that's how you would do the state space equations. But what if you were trying to do, okay, let me show you the direct form 2 again. I'll show you right here. Really simple, really easy. B0, B1, B2, plus, plus, plus. Yeah, you see how fast this is? And then this is just a wire, block, block, boom, 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 A1, A2. If you were trying to do the linear difference equations, well, this right here, this one's going to give you a unique node. It's going to give you some node. Let's call it Q of 2. Oh, oops. That's because my dock camera's not... because you know why? This is dumb camera thing. I hate it. There we go. It's ruining my space. Let's call this node Q of 2 of n. Okay? What happens when it goes through the delay? Gives you Q of 1. Or a Q of 2 of n minus 1. Okay? Right with the skinnier marker. Now let's look at this node right here. This node is also unique. It's going to give you something, okay, this plus this plus this. So let's call it Q of 1 of n. And then when it goes to the delay, what's the value right there? Q of 1 n minus 1. All right? So that means what's the first thing you got to solve for? Well, here's your x. Got to solve for that one. That's your input, x of n. It goes through here. What's the first thing that gets solved is this y of n. So solve for y of n. And then what's the next thing? Q of 1 of n minus 1, then q of 2 of minus. Does that help? Okay, and this one's the TDF2. So I'm literally doing exercise 1 again. And then because someone's probably asking, okay, this is feedback, feed forward. This is feed forward, feed back paths. As you can see, this feeds forward. Draw your arrows. This goes back. Let's do the direct form 1. And this one is the easy one too. Actually, this one should be the easy one. The delays are here. But I don't like drawing this one. B0 node B of 1. Should I? Okay. B of 2 delay plus, and then you have a C of n right here. Okay, plus y of n delay a of 1. This is getting really messy. Minus a of 1 plus delay d minus a of 2. So what I'm trying to tell you now is if you were a running man, right, going through the block diagram, the first thing it's going to go through is C of n. So this should be the first equation you should solve for. Put that at the first thing on your for loop. Then the next thing is your y's. And there's actually only 2 equations for the direct form 1 block. How many do you have for the direct form 2? Well, with 3 or at least n with 2 delay blocks, you have 1, 2. Okay, you have this q of 1, that's 1. Q of 2, that's 2. And this y of n. You have 3 equations coming out of that from the TDF2. And then for the DF2, you have, well, this is for the state space equation, sorry. State space. This is for linear. And this is also for linear. The cool thing about the direct form 2 is actually this can also just be Q, I'm going to call it Q L or something like that, N, okay? Why am I calling it Q of L of N? We're going to do linear. So when it's right here, right, what happens when we go through the delay block? Q of L minus N minus 1, okay? Right here. However, this also goes through the block diagram again. So if this is QL N minus 1 right here, what's the value right here? Q of L minus 2. It's just the same state being shared through the same node. Ah, makes sense. So that means you only have, if you wanted to, you only have 1 equation, 2 equations. This right here is y of n. 2 equations. Pretty cool, huh? Or you can do the 3 equations if you like. Oh, making unique nodes. This can be Q of L minus 1, Q of another. You can do that too. But this one flows. The same node gets flowed through the same path. For the direct TDF2, you get unique nodes because of these plus signs. And then this, well, you only get 2 equations because you're adding the feed forwards with the feedbacks. Makes sense, everyone? Easy? Does that help with getting the assignment done? And I still want it to be due 10 a.m. tomorrow, Saturday, so I can start grading them. So this assignment shouldn't take too long. If you go through the videos, I go through solutions more in detail, really in detail. Really slow too. But if you want to know if you're doing this right, from the last lecture, let me move this. How to check your answers. Use the filter function. So if you look at the ending of the implementation of linear difference equations, this right there is your solution, like the solution itself. Use this to compare your block diagrams. If everything looks, if all your y's look the same, and yes, do submit your M codes because I read through all your code and I run it on my own system too, just in case. Then you've completed the assignment. All the outputs should be the same. Make sense? There you go. So, I wanted to talk more about, well, what we were going to have on the exam, but I guess everyone is, a little shaken up. I guess everyone's still shook about the assignment. So this review right now that I'm showing, and that's what my biggest fear was, like, oh, we were going to go over the assignment, not the actual review. So I'm expecting everyone's going to get at least a 10 perfect on this assignment. But for the exam, hopefully an 11, I wish, but no, only maximum 10 points. But for the exam, what I would want to review for you guys is the following. And my notes are messy with page numbers, but I will show you one thing. So one thing, and let me pull this out. I don't even remember the page number. I think this should be
Probably 5 then.
should be 5. Yes, 5. Okay. So one thing is, suppose Dr. Stuber gives you, okay, he's giving you some y of, let me call it, of n, right? He gives you some value, and then he's going to make you transform it. So here's our x of, let's call it n. And what does he do? I'm trying to remember how he sets this up, which is equal to, I guess, x of, create a system. I don't know. Let me see. N minus n naught or something like that. So he might give you some random system. Like, okay, if you put in an input, what does this transformation do? Oh, the transformation says, whatever we put in here, do this. So he's going to ask you the following. Is it linear? And I think there are 2 conditions for when he wants in linearity. So the first thing is, okay, if I can multiply, so 2 conditions must be met. It's the scaling property and additive. So if I can add x of 1, or no, if I can multiply x of 1 by some alpha, right? Let me see. X of 1. How do I want to say this? X of 1. Let me write it like this. T alpha of x of 1, right? Can this be equal to just multiplying the output, directly the output? Okay, so this transformation, if we were to multiply alpha to this input, then this transformation gives us, well, alpha of x of n minus n naught. But if we wanted to directly implement this, well, what's our output? If we just look directly at what we have, well, that's also x of n minus n naught, and then multiply this right here. Are these two the same? If we go through the transformation, or if we directly multiply this gain right here to the output itself, do we get the same value? That means it is linear. Okay? And then additive is basically saying, okay, if I have 2 t systems, x of 1 plus x of 2, actually n plus x of n, this is bad right here, right? Can this be the same as if I were to add just 2 systems on its own? X of 2, right? So if you do this transformation, the result of this transformation into here is going to give you x of n minus n naught plus x of 2 n minus n naught, right? But if we just look at each individual block, it gives you the same thing. Well, I'm literally, look, this right here is y of 1, and this right here is y of 2. So if we just add 2 outputs together, that's what I'm trying to say. So just 2 outputs together to give us x of 1 n minus n naught plus x of 1 or 2 n minus n naught. So basically, can I say, if I'm an engineer, if I have a system T, one system, and I were to throw 2 inputs, x of 1, x of 2, and it's going to give me t of x1 plus x2, right? But let's say I'm a rich engineer. T and t x of 1, x of 2. This is going to give you y, and let's just put a summation block there. Y of 1 and y of 2, right? I want to just build two different systems from two different friends, look at the outputs, and just add them. So is this similar to this? Then it follows the additive property. That means this entire system is linear. So it is additive. I think is that the word? I think that's the word. That's what I would recommend. So therefore, it passes this condition. It passes the linear condition. That means it is linear. Since it passes scaling and addition properties. Okay? So that's one thing he's going to ask. He's going to give you a random transformation. Actually, what's this transformation? What is in this box? If you notice, it's just a delay. It's just a delay block. Delay. So he can model it as something like, oh, multiplication. Maybe he's going to modulate the time. Point is, can you do everything I'm doing right here on the exam? There's a lot of problems in the Shams outline and also in his book. Can you solve it if it's linear, if it's memoryless, if it's causal, if it's stable, stuff like that. So that's what he's going to ask. So I'll just rewrite that again. Okay, stuff to study for. Study linearity, causality, memoryless. And what's the next one? Was it stability or? Yeah, stability and stuff. I can't remember the other words, but linearity, causality, memory, whatever he said in class, there's like 5 things to memorize. 5. You can do all the math problems. Like, oh, like look, here's our delay. Well, let's see. Does it actually have memory? No, it doesn't have memory because it doesn't care about anything. Actually, this system right here, if you look at it, y of n, which is equal to t of x of n. X of n minus n naught. It already passes linearity. Causality is we can't see the future. So that means no pluses. So this right here is a minus, and there's no pluses. We have previous outputs, previous inputs, previous everything. We can't see in the future. So this passes causality. That's it. Basically, that's the practical definition. You can't see in the future unless you're a controls person. But man, we're not controls people here. Oh man, we're already past our time, but I want to go over this. Oh yes, the superposition. Yes, that's actually actually the word I was gonna get to. So yes, you can, instead of doing these two ways, like scaling and additive, you can do this one right. Actually, I'll show you. Linearity. You can do alpha of x of 1 plus beta of x of 2. I think is that the superposition way, like putting both of them at the same time? Yes, you can. I think it's one of the examples he does in the book. And then memoryless, does it store anything or something previous in time? I don't remember the definition of that. Well, this one, does it store memory? I gotta actually review that one. And stability, does it blow up? And that's where you have to take your integral or something like that. I think not the Schwarz inequality, or unless it could be. But you look at if this were to go to infinity, does it blow up or does it go anywhere? Actually, whatever input, as long as if you look at this, as long as our input is bounded, x of n is bounded, then y of n will always be bounded, as you can see from this delay. You throw in something, it doesn't blow up. But if you throw in infinity, it's going to blow up. So this is something I would recommend studying. Whatever he said in the previous video, study that. The 3 things that are going to be on the exam are going to be definitions, it's going to have do you know what a linear time invariant system is? Like, can you define what a linear time invariant system is? If it passes all this, then you have an LTI system. LTI system. Do you know what a system is? Do you know what a system is? Chapter 2 is systems. So can you do all this stuff? Can you define if it's a linear time invariant system? Got it? And the third one is block diagrams. Okay? Can you draw your block diagrams, both analog and digital? There's one thing I forgot to cover, and Dr. Stuber forgot to cover, but I don't think it's going to be on the exam because I think he's going to want state space equations, is what happens if you have integrators in your thing. So what I mean by that is, and this is going to be the last thing before we all go home, is instead of y plus dy dt, right, is equal to x plus dx, right? Sometimes we don't have differentiators, we might have integrators. So what we could do is integrate the entire equation. So this becomes y plus y. So integrate. So this differential, when you integrate it, just becomes y, and this becomes x, and then plus x. So then if you were to do block diagrams again, well, you would solve for y, which is equal to this x plus x minus as integrating y. And then you would do the process again, but with integrals. But I don't think so he's going to put that in the exam. So this is the integration way. So that's good to know. He told me to cover that for you guys a little bit, but that's literally that in a nutshell. Differentials, differentiators, or integrators. But I think it's going to be purely discrete systems for this exam. So are there any other questions before we go home? Before I end the lecture? So everyone's going to get their assignments done by 10 a.m. Trust me, I produce so much content. I really want everyone to succeed in this class. Like you saw me post those videos at 12 in the morning, 1 a.m., 2 a.m. It's because I really care for you guys' education. I put so much effort, even give you guys solutions. It's probably one of you guys saying, oh, he doesn't give the solution. Like, I'm trying to help you guys out. Not just do it for you, but make you guys understand what's going on. The assignment is here to help you. This assignment is literally studying for your exam. I don't know what he's going to put on the exam. He's going to throw in any block diagram, but I think it's definitely going to be discrete. So hopefully this is a good review session. Trust me, I think you guys will do really well, especially on that block diagrams. Definitions, if you have photogenic memory, I guess roll your dice on that one. And can you define what a linear time invariant system is? Chapter 2, systems. Make sense?
Thank you.
Perfect. And then hopefully next week we're going to start chapter 3, which is, well, convolution, which is going to be really exciting. All right, everyone. That's where we end the video. All right, take care.